Okay, one common mistake in computing derivative of exponential function is this, right? Is this one. Is you try to apply the power rule here so that you get, sorry, there. So you apply, okay, a multiply by the power, which is x, and then reduce power by 1. Okay, so this is common, the common mistakes. How this is. So this is applying power. Okay, so the thing here is that this is exponential functions, not power functions. So e to the x is exponential, not power. Okay, so let's try to distinguish this one here, a to the x and x to the a. Okay, so x to the a, this is what we call a, uh, say, let's power. So when you take derivative, take derivative, let's say again, x to the a, the variables here, a, the power a is fixed. This is variable, this is fixed. Okay, in this case, you get, that's true, that the multiply by the power and reduce the power. Okay, but in this case, you see, this is the variable. This is the fix. The base is fixed. Here, the base is variable. Okay, this is what we call an exponential. So in exponential, we have this rule. So again, you get this one, the exponential, and times the ln of the base. You see? That's the difference. Okay. So I would like to uh, say a types of exponentiations. Let's see. Types of exponentiations. And their derivative. Okay. So the first one, the simplest one is, say, just a type, or make it a table. Type derivative. Okay, the first one is just A to B, where A is constant, B is constant, right? So like 2 power 5, 2 power pi, okay? But that's another constant. So derivative is always 0. Okay, so the next one is power. Um, so the derivative is like polynomial. Okay, so power type. So derivative is just a x 1. So just, okay. And the third is what I would like to call, say, not would like to call, but this is called the exponential. Okay? And the derivative is just okay. So you see, this is increasing in complexity. Okay, so this constant power constant, variable power constant. This is constant power variable. And then the next one is, what about this one here? X times X. So both are variables. Uh, the book, Purcell doesn't give a name to this one. I would call this super exponential. And the derivative, let's see, how would it take the derivative? So for example, y equals x, x, okay? And if you apply ln to both, you get x ln of x. All right, is it clear how we get x ln of x? Let's just do step by step. So x factors out. All right. And then you take the derivative. Remember this trick? Logarithmic differentiations. Okay, so this is because the chain rule, so you get and then x ln of x. So derivative of x just ln of derivative ln of x is 1 over x times x. Okay, so y is y prime. Just write this down, not to confuse this. There. So this gives you y again. There. Okay, so that's give you this one. X to x. Again, you have that super exponential multiplied by something else. This factor here. Okay, you don't have to memorize this one. Just remember to recall how to apply that log diff. Okay, so using log diff, actually you can derive this power rule here. So this power functions. If you apply ln, so a factors out, and you take d dx, so this prime, a times ln of x, this. Yeah. Okay. And so here we have a over x times y. Y is x to the a. Okay. Let's simplify this a little bit. A, x. So this is power 1. There. So you get this power rule. Okay. So actually, that's a log diff is a very neat trick, actually. Powerful trick. Okay, so this is type of exponentiations. So one example is this one here. Let's compute x times cosine x whenever this is defined. Okay, so let's compute using log diff. So let y equal sine x, sine x. Okay, so ln of y is just cosine x times ln of sine x. Okay, and when you take derivative of both sides, on the left hand side you get this, and then the right hand side, well, just the product rule. Derivative of cosine, that's negative sign. Okay, and then plus cosine times derivative of this. Derivative of log sine, ln of sine is 1 over sine times derivative of sine, which is cosine. Okay, so y prime is just the end. Again, this is sine x. Okay, multiply by this is, let's just write this down, cosine square x divided by sine x minus sine x ln of sine x. There. Okay. And one more example is, how about ddx of x to the x to the x? Well, this is what I call super exponential. Okay. So let's do this one. Let y equals x to the x to the x. So ln of y is just, let's see. Okay, so let's tells you. We still have this one here. Let's do this one. ln of y. Okay, so you get ln of x times ln of, okay, and this gives you just ln of x plus ln of let's see, can we uh, oh yeah, I don't need to do this one. X just X times X factors out. There we go. Yeah, okay. I do. Oh, we compute already here. The x to the x is just, we compute already. Sorry, x square, x to the x, 1 plus ln x. So let's just compute this one. X, this is y prime times y. So this just gives you ln of x to the x. Okay. And x times uh, derivative of ln x to the x. So derivative of ln x to the x is just 1 over x to the x. Derivative of ln of x. There. Okay. So you get this cancel. Okay, so y prime is y times this. All right, so this example of derivative, what's it called, a super exponential. So it is possible to do log diff, using log diff to compute. Questions? All right, so that's the end of the sections. Okay, so let's do this one. Exponential growth and decay. Okay, so So this relates to some physical problems, and we use exponential to describe it. All right, so for example, law of all population growth. Okay. Uh, all population growth is basically says that the growth rate of populations at times t is proportional to its size. So, for example, here, uh, so what does it say is, well, what it says is that the growth rate, suppose P of T is the population size at time T. So the growth rate is the rate of change, of course. So, so that's dp over dt. Okay, so that's proportional to the population size. Okay, so replacing this a proportional, what it means is that dp over dt is for some constant k. Okay, so that's how we solve this one here. Okay, so how to solve this? Now it's become differential equations. All right, so we learned in the past chapter, previous chapter. So we start with this. Okay, and let's separate the variable. So what we have the letters here, just P and T, right? Okay, but K is constant. So P and T, just put P together and then T on the other side. So we have here, okay. So that's uh, the 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 trick. And let's do integrate. So if you integrate, okay, so what we have is just, this is just gives you ln of t constant. You can put the constant just once later, k t plus c. Okay. Uh, but here, because the um, p is the always non-negative. This is population size. Size is non-negative. So Absolute value is just p itself. Okay, so then it's just ln of p. And take exponential. So this just tells you p equals, sorry, p equals k, p plus c. So we'll take exponential. So this gives the exponential cancel the ln. P is exponential qt plus c. Okay, so I would say this, but this is constant. So let's just write this down. Okay, so we have uh, populations as, yeah, let's give you how we find c prime, sorry, c tilde and k. Well, we need a data to find k. All right. So let's take a problem. Take one example. So this is of this one here. Okay, so this in the beginning of 2004, world population is 64 point billion. By 2020, it's, so this tells you that, uh, say, assume this is t equals 0. Okay, so t is 0 is 6.4. Okay, and the question is by year 2020. So this is 16 after this one. T equals 16. Okay, so this tells you that P16, the prediction is 7.9. Okay, so that's our data. Okay, so that's given data is P of 0 is 6.4 and P equals P of 16 is 7.9. Okay, so we need to find C and K. Okay, so plug in this P0 and P16 to this one. So P equals 0. T equals 0, that means T equals 0, that is, because it's just 1. Sorry. Oh yeah, P0, this is e to the 0, just 1. is 6.4. Okay, so that because it's 6.4 is okay, so P of t after this data, we know this should be 6.4 into kt. So we use this P16 to find k now. Okay, 6.4 k16. Oh, sorry, this is 7.9. All right, from here we get e to the 16k is just let's see, 7.9 over 6.4, right? So apply ln both to get this becomes ln. So it should be ln. Okay, so k is 116 times ln. This is more than 1. So that's why this is positive. Positive means growth. If negative means decay. Okay. So for example, the question is here's the questions. When that's double of uh, okay. So you can check this with double. All right, so to double the populations, so now to double, what you get here? So your E is E to the say this is 16, double this 6, okay. So this tells you that the P of T is 6.4 e to the P over 16. Okay, so this tells you that e to the P over 16 of Ln is just this is double of this, which is 42. Okay, so T here is this solve this one. The Ln of 7.9 over 6.4 equals 60. Ln of 2 times 16. There we go. Okay, so you get this one. There we go. That's the double time. This is what you call doubling time. Okay, questions? Okay, if not, then I'll stop here and then we'll continue this tomorrow with the decay, this doubling time. And we'll do the what you call the differential equations. Skip this one. Yeah. Stop here. You will have the tutorial later on at 2. So exercise for this chapter. Okay, any questions?
No questions.
Right, so let's stop record.